Hi everyone, today we're going to have a go at graphing a root function using y squared equals x as the basis. That's our goal for this video. Now, the first thing to acknowledge is that we're going to use, actually before we even start using y squared equals x, we're actually going to go a step before that and use y equals x squared to have a little investigation here. Now, if I draw a very nice little basic y equals x squared, just my parabola, concave up, passes through the origin. Now if I start to think about y squared equals x, what it ends up looking like, I'll show you why in a second, but it ends up looking something like this. Now that's what we call it, the inverse function of y equals x squared. An inverse function is essentially where we switch x and y, and what ends up happening is this gets mirrored, our black line gets mirrored in the line y equals x. So our black curve gets mirrored in the line y equals x, which is that line there. It gets reflected in that. Now that's the red line is the inverse of the black line. It's a whole topic we do on inverse functions, so we don't need to focus too much on that right now. But I do want you to see the shape of our red curve there. We'll notice it's a right-facing parabola rather than an up or a down type one, which means it's actually not a function. Okay, the way that I have drawn it there, it is not a function, and that's okay. There's some things we can do to make it a function, but as it is there, it's not a function. Let's have a look at a table of values for y squared equals x and see why it ends up looking the way that it does. I've drawn up a little table of values here for y squared equals x. You notice I've been very selective about the values I've picked for x here. I've picked something that when I take the square root of it, it's going to give me a nice rational answer. It doesn't have to be that way. You could go pick 0, 1, 2, 3 if you would like. These couple of numbers here prove a little point about something I want to explain in a second. But that's neither here nor there. So let's have a look at what happens here. Well, what I'm really solving here for my first value for x equals 0 is I'm solving y squared equals 0. Okay, this is a little bit different to what we're used to, yeah? We're used to solving an equation that has x as the subject, or that we're trying to make x the subject. But here we've actually got y as the subject, well, y squared as the subject, and we need to find our values for y. A little bit different. Now, if y squared equals 0, that means y equals 0 as well. But if y squared equals 1 over 9, if I take the square root of 1 over 9, I get 1 over 3. But I've actually forgotten something pretty important there. I've forgotten that if I take the square root of something, I have a positive branch and I have a negative branch. Or I have a positive value that can give me 1 over 9 and a negative value that can give me 1 over 9. So that means I've actually got plus or minus 1 over 3. The same deal with when I take the square root of a quarter, I get a half. Half times a half being a quarter, but it's the positive or the negative of a half. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 4. So what we're used to with a parabola, normally as x gets bigger, y gets really, really big and very, very fast. But actually the opposite is happening here. X is getting very large and y it's increasing, y is going up as our single increments here, from 1 to 2 to 3 to 4, but x is getting much larger. Okay, so we've actually got quite a flat curve happening here. Now if we have a look at when we graph this, passes through the origin. That's the origin, the y-axis there is not an asymptote. We can hit the y-axis because we can take the square root of 0. That's absolutely fine. Now if I go to x equals 1 over 9, really small value, I go to about there, 1 over 3. But I also go to negative 1 over 3 as well. And when I go to a quarter, I go up to a half, or down to negative a half. Starting to see why we end up with that parabola, that sideways parabola shape, right? Plus or minus 1 for x equals 1. I go across to x equals 4, and I end up with plus or minus 2. See what I mean? We've gone a long way across, but a very small amount up there. It's got a very slow rate of change. And I go over to 9, I end up at 3 or negative 3. And I've got this shape here. Haven't passed through my point perfectly there, but you get the idea with the shape. Now I want to focus on these points in here. These ones here where x is less than 1. Okay? If x is less than 1, what we actually end up with is a scenario where f of where f of x, if I take the square root of f of x, that's actually bigger than f of x. All I'm saying there is that the square rooting a number that is less than 1 actually makes the number get bigger. Square root of a quarter gives me a half. Half is bigger than a quarter. Square root of a ninth gives me a third, which is bigger than a ninth. As soon as I go to 1 or larger, the square root of 4 is not bigger than 4. The square root of 16 is not bigger than 16. That only occurs when x is less than 1. And I'll actually caveat there with between 1 and 0. Okay, because of course our curve here actually has a domain of x must be greater than or equal to 0. Okay, and it's actually got a range of all real y. And I should really write there all real x, x is greater than 0. And that's for our basic y squared equals x. Now there's actually two parts to our curve here that we've drawn. Part 1 is y equals root x, and part 2 is y equals the negative root of x. Now that's not me taking the square root of a negative number, that's me taking the square root of a positive number and then getting a negative result. So this one here is our negative values, or if you'd like, that's where the y values are negative, and up here is where the y values are positive, given by the same set of x values. Now, by the way, I think I've already mentioned this one, I'm going to show you with a little vertical line test. It is not a function, because I have two places where my black dotted line there hits my curve. But if I go just look at y equals the square root of x, just looking at the green part there, that is a function. Same deal with y equals the negative root of x, which is the yellow part there. That's a function. But when I put them together and graph y squared equals x, or if I was to do it together and say y equals plus or minus root x, that's not a function. It fails my vertical line test. It is no longer a function. Some take-home points here before we look at one or two examples. So the square root of f of x, or as our really basic version, y equals root x, will only be defined if fx is greater than or equal to 0. Okay, we cannot take the square root of negative values in a real number context. If we're looking at complex numbers, we can do that, and it becomes, as the name suggests, a little bit more complex. But in our real number system, we cannot take the square root of negative values. So we're only going to be taking the square root of negative numbers. So that means we're going to end up with typically a domain here, normally, of x must always be positive. Now, there's some curves where we go and do some funny things with them, so that domain changes a little bit. But we are only going to be taking the square root of of positive values there. We cannot do that for negative values. Now, as I said before, if fx is less than 1, but bigger than 0, so between 1 and 0, what that means is the square root of fx is actually greater than fx. Basically, if I square something that's less than 1 but positive, it gives me a bigger result. And looking at one more thing here, if fx is greater than 1, so if fx is equal to 1, that means the root of fx is equal to fx. And third scenario, if fx is greater than 1, that means the root of fx is going to be less than fx. And we saw that on our last graph, right? When I went and took the square root of a quarter, I got a half. It got bigger. When I took the square root of 1, it stayed the same. And when I took the square root of 4, it became 2. It got smaller. So those three scenarios there's 1, 2, 3 dot points, are really just an example from the table of values there. They're just a way to generalize that table of values, what we observed there. Let's have a look at a couple of examples. I'm going to take fx equals x minus 2. Straight line that looks something like this. Pass through 2 and negative 2. And then what I want to graph is I want to graph y equals the root of fx and y squared equals fx. and see what those two look like. Okay, so straight away, for our first scenario here, y squared equals, in fact for both scenarios as well, anywhere where our function is negative, where f of x is negative, I can ignore, because I'm going to try to take the square root of those negative values. Okay, for example, if I take this point here, that is the point 1, negative 1. Okay, when I go put 1 into my function, I get negative 1 out. When I try to take the square root of that negative 1, I get a complex result. I get an imaginary result. It's actually I, which is the square root of negative 1. But that doesn't exist on our root function. So what that means is, let's completely start again here. When I go and start graphing my root function, I know it starts from here at 2. Because everything to the left of that meant that my y values were going to go negative. I can't take the square root of those. They are a no-go zone. Now, what we need to find here is actually, we need to find where f of x equals 1. And that's actually pretty easy to do here because 3 minus 2 equals 1. So at this point here, I've got this point, sorry, that x value there, I've got this point 3, 1. Now what that point is, where f of x equals 1, that means the root of f of x also equals 1. So I'm going to take this here, I'm going to get rid of that and say this is where my curve's going to go, and what we're going to have this shape up here like this. Okay, now what actually happens here is in this bit here, I'm moving quite steeply, and then this bit over here I flatten way out. Okay, and if we were to put our original line back on there, and let's just put this part of our line on, not the whole thing, what we find is that black is above blue in here, but then blue is always above black out here. And our key for that is where we pass this f of 1. I'm sorry, f of x equals 1. Where we pass that, our root function becomes flatter, and our original function continues to go higher. Because the square root of anything bigger than 1, of course, gets smaller, which is why black is below blue for anything bigger than x equals 3 here, which is f of 1. That's that point here, that x value there. Now, that's our first one. This black one here is y equals the square root of fx. If I want to then go and say, now I'm actually going to do this one, let's recolor it. I'm going to say, now I want to graph y squared equals fx. Well, it's actually the same thing, except this time it's actually got 2 branches to it. It's exactly the same one, I'm just slightly offsetting them so you can see they are different. And then I've got this one that's down here. And this one passes through 3, negative 1. Now that doesn't mean I'm taking the square root of negative 1. That means when I go put 3 into my function and I get y squared equals 1, I can have y equals positive 1, which is the up version, or y equals negative 1, which is the down version. If I graph this one, it's just going to have 2 sides to it. If I graph just this one, it's only going to have 1 side to it, but they are reflected in the x-axis, sort of like when we had a look at those absolute value graphs where we reflect something in the y-axis. It's a similar thing here where we reflect something down in the x-axis if I square the whole thing as opposed to taking the square root of the whole thing, even though they're based on the same graph. Let's have a look at one more example. This time I'm going to look at f of x equals x squared minus 4 and see what that looks like. Okay, and of course I want to graph y equals root fx, and I want to graph y squared equals fx. Once we've done the top one, the bottom one actually becomes really easy there. So let's start with a little graph of y equals x squared minus 4. Looks something like this, and it passes through 2, negative 2, turns at negative 4, and we've already got enough information there. So let's go back to our basics here. When I take the square root of something, by the way, once again, I'm taking the square root of y values here. I'm taking the square root of x squared minus 4, which is our y values on this original function here. So anywhere where my curve here is negative, all in here, that can be ignored because that does not exist. Okay, this will have a restricted domain, and its domain will be all real x, x greater than or equal to 2 or less than or equal to -2. Between 2 and -2, our root function does not go. And that doesn't matter whether we do this one or whether we do this one that's got the 2 branches. Still doesn't go between 2 and -2. Restricted domain because I cannot take the square root of a negative number. Let's see what happens here. Now I know that I've got my values of 2 and -2, and in between here we've got our no-go zone. That's 2 and -2 are not asymptotes, they're points, they're fine because the square root of 0 is 0, and when I put in either 2 or -2 I get that 0, so that's fine. But what starts to happen here is we end up with something that looks like this. If you'll recall, our original function looks something like that and that, with that middle chunk taken out. Now what happens when I graph y equals the square root of x squared minus 4? We turn somewhere like this. Something like this. And they should be at the same height there. They're just not amazingly drawn. Now, and what ends up happening, they meet at this point here and at this point here. And what we need to do for those, we need to find where f of x equals 1 to do that, which is at x squared minus 4 equals 1, which means x squared equals 5, or x equals root 5, or negative root 5. Because again, our original function, y equals x squared minus 4, and the square root function will meet where y equals 1. Because when I take the square root of 1, it's the only place where that's equal to 1. Now, so that's what our graph looks like here. And of course, once we get past root 5, let's take x equals 3. X equals 4. Well, if x equals 4, 4 squared is 16, minus 4 is 12. So up here I've got this point 4, 12, whereas down here I've got this point 4, root 12. Root 12, a little bit bigger than 3, or about halfway between 3 and 4, but it's definitely smaller than 12. So we can see that our root function is much flatter, where our original function was much steeper. They meet at our x-intercepts, and then at this point here where y equals 1. Now, if we have a look at this, this second version here, we're on y squared equals fx. Well, it's exactly the same thing, except now I add in this negative branch as well. And again, these down here, these may look like they're getting flatter and maybe approaching something, an asymptote. That's not true. Okay, there's no asymptote down here. It's just increasing at a very slow rate. Okay. Got one more I'd like to look at. I want to have a look at y equals 1 over x. See what happens here. Okay, of course 1 over x looks something like this. It's got two asymptotes, both axes are asymptotes. Now when I go sketch these, and they pass through this point here, -1, -1, and 1, 1. Those are key here. Now if we have a look at this, anywhere where y is negative can go. Okay? Anywhere where our function is negative, not where x is negative, it just so happens here that I've got rid of the negative x values. That is coincidence. If I was to shift this curve 5 units to the right, I would still be getting rid of everything that is below the x-axis, not just because x is negative here. It's a simple coincidence. Now, what ends up happening when we take our square root function? The shape ends up looking pretty similar here. Now, let's think back to this. Where y is less than 1, our root function is bigger, because when I square root something less than 1, it gets bigger. So it's something like this. All these values here, our root function is going to be bigger. But when y is bigger than 1, they end up being smaller. Something like this. And what we end up with is a curve actually that ends up doing something like this. And what that means, by the way, they meet here at 1, 1, which is because when y equals 1 over 1, that's 1. If I then go take the square root of 1, still 1. Of course, that y value of 1 is really important for us. That's because it's where our original curve and our root function meet one another. Now, if I want to go and add into this, so this one here was y equals root of 1 over x. Now, if I want to go graph y squared equals 1 over x, I hope we've picked up the pattern here that if we're asked to do this one, it's actually pretty straightforward. We just take the exact same thing and do something like that. It's probably actually got to be a little bit more detailed. It might even be worthwhile using sketching another green line in there as a basis. But of course, that's the point 1, negative 1. Now, we can have negative y values here because if I take my values for x and put them in, I can square root them and I end up with a positive or negative mirrored y value there. So that's what ends up happening with y squared equals 1 over x. I hope this is making a little bit more sense now. We can see what happens if I take the root of something or if I graph y squared equals something as well.